Now I wanted to actually talk a bit about the microbit. And I think everybody probably has a superficial knowledge of it. If I was to title this as a standalone lecture, this is everything I've learned about the microbit as somebody who both designs products for it and has taught with it. This is going to be a little bit of the nitty gritty of it, but I think it is helpful for teachers to know these things because you will run into weird problems when helping students code to the microbit. If you understand some basic things about the microbit, it'll be very helpful for you. This is the part everybody knows. The microbit's amazing. It works with multiple software platforms. You can code to it in various languages. Over almost 60 million students worldwide have used the microbit. One factoid a lot of people don't fully know is if you look at this logo on this page, you'll see there's a tiny little BBC microbit above it. Why does it called the BBC microbit? This was actually initially designed in England to give to every middle school student as a way of teaching them coding. Those of us of my vintage will remember the Sinclair. There was also a computer given to all students in the early 80s that the BBC subsidized that was also designed to teach everybody coding. And I think it was a Sinclair or a variant of the Sinclair. And this was the BBC. This is them trying to revive that. So the biggest takeaway I would say as to why this matters is because at every turn you will notice that the microbit is very much designed from the ground up to teach. It has features in it that are specifically designed for the teacher's workflow, for teaching, and for how things work. And that's why it is such a powerful tool in the classroom. It is very much following that philosophy of low threshold, no ceiling. It's designed to be easy to implement. If anybody has worked with Arduino before, all the things that made Arduino a pain in the ass are not there. It's web-based, and when you plug it in, it's recognized automatically as a hard drive by your computer, so it doesn't require any special drivers. You can even upload programs off of a tablet. It has really optimized the workflow. You'll see there's a lot of very positive things to it because of that. And that's number one. One other thing, the difference between a microbit, a Raspberry Pi, or a Pi Zero, the microbit is a programmable microprocessor on a board with extra stuff with it. What does that mean? It means it is a single-use processor that you can program. The Arduino was the first one that you could program to. You could do very easy digital work on it. When the Arduino came out, it was revolutionary in what it did to make it easy for people to program a microprocessor to do what they wanted. For engineers, it took something incredibly complicated and made it much easier. Unfortunately, in a classroom setting, it's still a bit high in the bar when you've got a large classroom, and lots of things can still go wrong with an Arduino. I'm not an Arduino hater. They're very great. They're very powerful things. But the fact that it was designed with engineers in mind and it made their life easier. The microbit is a programmable microprocessor designed with teachers and classrooms in mind to make their lives easier. So it covers that last little bit that makes a huge difference for a classroom. A Raspberry Pi is actually a full computer. It is not a programmable microprocessor. It is a full computer that is running as a computer. A Pi Zero is a microprocessor. Same as the Adafruit Circuit Playground is a programmable microprocessor that you can code to, just the microbit. What's nice about them is in some ways they're easier to use. You upload your program, when you turn it on, it runs your program. In a Raspberry Pi, you turn it on, it boots up, and then you have to get in there, and if you don't have it with a script to automatically start running your program, it's just running a version of Linux, and it's a small computer that you have to put a keyboard and a screen on. So that's a high-level, big description. This isn't a discussion about the different microprocessors. If somebody is interested in that, and if there's enough interest, I'd be happy to dive into the differences. But we're talking about the BBC microbit, so I want to keep us focused on that and what it is. So if you go on their website, you can get this blown-up drawing of what the microbit does and what it has built into it. So as I said, it's a programmable microprocessor. that has a lot of built-in features. The processor is this little square here that you can program using MS-Make Code or any one of those programs. In addition to just having a processor on there, it has what are called these pins. These pins are used for controlling other objects, either with an analog or a digital signal. It has a lot of built-in things. What's nice about the built-in stuff is that you can do a lot with just the microbit and then focus your energy and your students' energy on their coding and not on their making. I talked about that triangle of your objectives. A lot of projects in the Arduino end up being dragged into troubleshooting and making because you need a breadboard, you need to connect this wire to that wire, you need to do all these things. And they end up being lessons in perseverance, which is great. It's a great lesson, but it shouldn't be the lesson of every one of your projects. And that would happen with the Arduino. And it's something that you can completely avoid when you have things built into the board. So let's talk about what is built into the board. This is a picture of the Microbit V2. I'm assuming everybody has V2s, but if not, that's fine. I'll highlight the things that aren't in the V1. The easiest way to tell what kind of board you have is if you don't have these little ridges along the bottom, you have a first generation microbit, a V1. What are the big differences? The ridges, like I just said. Both boards have two buttons built into it. They're labeled with a tiny A and a tiny B. Both boards have an array of 25 LED lights. These LED lights can be programmed into various shapes. You've got this matrix of 5x5 LEDs. The microbit also has a light sensor that you will see in the code. The light sensor is actually using the LED lights as a light sensor. So an LED can sense a charge when a light shines on it. It almost like reverses a charge through it. And that is how the light sensor works. Why do I mention this? Because both the LEDs can be a part of your project and art, but also a sensor. If the LEDs are on, they may affect your sensor readings. You may sometimes get weird readings from your light sensor if you're concurrently programming the lights to be turned on. One of those little quirks the Microbit has done to save costs is their form factor. It's small. As a manufacturer of products, the size of the PCB, you pay for real estate. So the smaller the PCB, the cheaper it is. I've saved cost by size. Where does this affect us? Another way you save cost is you reduce the number of actual components you put in. So rather than have a separate light sensor, they have used the LEDs in a clever way to be their light sensor. The V2, and this is not in V1, the logo is a capacitive touch sensor. So you can touch the logo and it can sense that you've touched it. The old one had two tactile inputs, A button and B button. The new one has three tactile inputs, A button, B button, and the touch logo. So you can touch the logo. It's a capacitive touch sensor. It senses that it's been touched, and that can be used in your projects. Somebody has done a clever project where they use conductive tape off the touch logo that then you can put on the arms of this TickleBot. Then when you touch the conductive tape, it triggers the TickleBot, which then triggers a servo. You can extend that capacitive touch sensor with something else. If I put an alligator clip on there and it's touching the touch logo, I can then touch the alligator clip and now I've created another input. So it's a very clever, interesting thing to do. It also has this microphone indicator, which tells you, if you look on the backside, there's a microphone. The microphone is also a V2 only feature. The microphone can register a sound level, but it can also be used for recording short snippets of sound. So you can actually record things with this microphone and then play them back. It is a very low audio quality, and it's actually one of the reasons my boards have an audio jack for output, because one of the reasons the playback will sound particularly bad is if you look on the back of the microbit, this speaker, it's a piezo speaker and a reasonably low quality speaker. It can do a pretty good amount of stuff. And if you dive deep into the sound library of the microbit, people have done some amazing stuff. Some hardcore synth have built entire synthesizer libraries for this thing. And you can really get some pretty interesting tones out of the microbit if you want to. For students who are really into music and sound, it's actually surprisingly good. The Microbit does have an accelerometer built into it. An accelerometer senses the force of gravity in 3 axes, in the X, Y, and Z axis. It knows what the force of gravity is on the Microbit. For those of you teaching physics, it can be a little complicated, but it's not undoable because it is sensing the force of gravity in that axis, and it assumes that flat is like this. In this axis, the Z is 10. So at rest, it's at 9.8. It's sensing the G-force on the board. So that can be a little confusing. Like at rest, it's sensing a force of gravity on it. The accelerometer is also used in the Microbit when calculating their blocks for pitch and roll. So the Microbit does not have a gyroscope built into it. It uses the accelerometer to sense pitch and roll. Why does that matter? Let's say you wanted to measure both the angle that the Microbit is at and the acceleration of the Microbit. You really can't do that because the angle that the Microbit senses it is at is based on it assuming it is stationary, and it's saying, based on the forces I am feeling now, I am at this pitch and at this roll. So if I know that perfectly flat, I'll have 0 force in the X and Y, but only force in the Z. If I slightly angle it, the Z will change slightly, the X and Y will change, and therefore I can calculate my precise angle based on those new set of forces. If you're doing more advanced coding and you want to concurrently take an angle measurement and an acceleration measurement, you're going to get weird results because of that. I've done projects with students where in trigonometry, they can use this as a way of getting very precise measurements for measuring angles. If I look through it, I put a straw on it, I can get very precise measurements of the angle that I'm looking. And I also have that compass. So I know my ordinal axes and I know my angles, my pitch and my roll. So you can do some pretty advanced trig and build some cool projects like that in math using that accelerometer. One more thing. Another area where the Microbit was clever in its design. There's this thing in computer science and in coding with hardware called a pulse width modulator. Think of it as an internal clock that is used to digitally change certain things on the pins or on your output. And it's almost the equivalent of if I want to change the voltage on a circuit by turning a potentiometer, the PWM is this clock that tells it how fast to give power to it and to do certain things. And it's used for making sound, and it's also used to control motors. Why do I go down this kind of weird tangent? The same clock, and I think of this as you've got this marching band with the person in the front keeping the beat, is being used for the sound and for the motor. If you concurrently run a motor while playing sound, you might get some weird results. You might see the motor stutter when the sound changes or when different things happen. You might get this weird acceleration and deceleration that's not in the code because it's using that same timekeeper to control both. When you know it, you don't pull your hair out trying to find out what's wrong with your code or setup because it's how they built it. I do want to talk about one last thing that I find incredibly helpful with the Microbit. If you look at my boards, they use something called an edge connector. The edge connector lets you take advantage of the fact that while the Microbit makes it easy to access these 3, 0, 1, and 2, the Microbit actually on paper has 20 pins you can program to. So you have 20 different ways of controlling external objects with the Microbit. The only way to really access those is any board that uses an edge connector. I always Google Microbit pinout and you can see exactly what pin does what and how you can program to it. I want to highlight 2 things related to my boards. Number one, if you're using another board, let's say, that drops onto a breadboard, and then your student says, I want to use all 20 of these pins and do clever things with these 20 pins. It gets a little complicated because you'll notice, for example, that pin 10, 9, 7, 6, 4, and 3 are also connected to the LEDs. So they have these columns. These columns are actually set up in a matrix and connected to the LEDs so that they're controlled that way. They've created a way of controlling the LEDs by creating a matrix among the pins to do this. Why does that matter? If I try to control a sensor with one of these pins that's also talking to the LED, I'm going to get weird results because that LED pin is wired physically through to those LEDs. Since that LED can also pick up a charge as a light sensor, it might sometimes give me a weird reading if my microbit is exposed to light. I might have this connected to a temperature sensor, but every time the sun shines on the microbit, I get a different reading, even though I'm not using the temperature sensor of the microbit, I'm using the temperature sensor of the external sensor. So I try to avoid those. The bit explorers, on the back, you'll notice that the pins available, none of them are 3, 7, 8, 9, 2, or 1. You'll see that pin 5 and pin 11 are actually connected to the buttons. So if you are trying to program something that uses those pins, that's fine. Just remember that's already connected to the button, and therefore you can't really use those. This image I showed is of a V1 microbit. Some of these other pins might be connected to different things, but it's good to pull up the pinout diagram because when you start to get to more advanced coding and you have these really head scratcher troubleshoot issues, it's probably something about the microbit, not about you. It can do a lot of very advanced things. You're more likely to step on the toes of the advanced things when that happens.